你们如果考我的考题的话，不太容易，就是你课本里头的习题就是一模一样的出来，所以somehow你要懂里头的东西，才容易去解里头的问题。所以上回我们介绍，就是在磁场碰到一个物质的时候呢，物质会受到影响。哎，那这个物质里头，显然这物质里头有磁场。So if you have a magnetic field nearby a material, the magnetic field inside this material will interact with this outside external magnetic field. 这个里外的两个磁场互相影响，那所以呢，最后的这个互相影响的结果 ，the net magnetic field is going to change. OK， 那在我们之前学的这个真空里头 ，in vacuum, we have curl of B equal to permeability, vacuum permeability multiplied with some current, and this current will generate this magnetic field. But if you have some material nearby, and this material has a lot of current loop coming from circulation of the electrons, or coming from the spin of charges inside this material, this magnetic field is going to give a force to those very small current loop, and when this current loop experiences a magnetic force, there's a torque associated with it, right? M cross what? M cross. This is proportional to the M cross B. Okay, so there's a force that is going to rotate those current loop and realign the small magnetic dipole inside this material. Therefore, you have to take into account the additional current generated, the additional current coming from those small current loops. So you have to add one term to this formula. And this comes from the magnetic dipole. OK， 那所以呢，这一项很重要。那之前我们定义的一项，这个 magnetization, that is equal to the volume average of all the magnetic dipole. Okay, this is the volume average of the magnetic dipole. It turns out that this Jm is equal to curl of this magnetization. Okay, in the volume. So we have to modify this vacuum expression for the magnetic flux density and add this term into your consideration. 因为这一项来自这个额外的电流，会让这个最后的这个值呢有个改变。Okay, and previously we derived the relationship between magnetization and the magnetization current, and one in the volume you have curl of M, and differentiated on the source. It's going to give you J. This is a volume current density. So think about that you have some magnet. You have some magnet and you have magnetization. But on this surface, you also have a surface current. that give you GMS. This means that on the surface you can view this magnet as some sort of structure that has a coil around it, and on the surface this is equivalent to have some sort of surface current. Okay, if this thickness, let's call it dz, then the current is going to be equal to the JMS multiplied with the thickness of this dz, if this is around z direction. Okay, and if you have a homogeneous magnet, if the magnetization inside this material is homogeneous, this means that if this m is not a function of coordinates, 跟这个坐标无关的话，就是它就是一个 constant 的话，那显然这个 curl this curl of m can be 0 in the bulk. 在这个 magnet 里头可以是等于0，这个 m 它是一个 uniform magnetization, nothing to do with the coordinates. Then if you look at one point inside this material, then this differentiation can be 0. Okay, so now you can really model a magnet with some coil around it and having some current moving around this coil. Okay, so previously you have solved the problem for a current like this or a current like this, and then at some z point you have some B field with some current right here, right? And this expression is in your handout in your textbook. So 之前你已经学会这个 B around z direction is equal to something like well, I cannot remember it. Z square, B square, 3/2 I think. 然后这里有一个什么 something to do with I, mu, and I think 这里是多少 ？B 的这里必须是 B 的3次方吗？不太像。林雄，这是多少 ？Anyway， 平方的话呢，这里是2/3次方吗？这是 B 的平方乘以2。Okay. So anyway, something to do with this. Okay, now you can actually calculate the B field at this location by dividing the surface current into many loops and add them all together. Okay, so if you want to solve the B field somewhere at this location, you simply divide all the surface currents into small current loop, and then now you have, if I just borrow this equation, and then I have dBz equal to B square mu naught dI, and then 2, if I look into a current loop at this location, suppose that I have a coordinate. Z is equal to 0 right here. And I'm looking at a position at, say, at this location, I have Z prime. Then the distance from here to here, suppose that I'm looking at B field from here to here, called D. Then this current loop is going to have a distance from this point equal to from here to here, so it's D minus D prime. So I have D minus D prime square cross B squared. Suppose that the radius of this is B. Okay, and then again, this is 3/2. And this DI is right here. You know that your surface current is this big, JMS. Okay, so you just replace this as JMS dz prime. Do this integration. Okay. Now we have to find out what JMS is. It's written right here. As long as you know the magnetization of this magnet, you can calculate this JMS according to this. Okay, this AN, now you know this AN is AR along R direction. Suppose this N is some uniform magnetization M0 around Z direction. So you do this calculation to get M0, and then you have AZ cross with AR. This gives you A phi. AR cross with AZ. Yeah, this gives you A phi. So you have a current going around this. Okay. 所以呢，你有个 B field 在 Z 的方向上头，所以这里呢，你可以进一步的再把它这个地方再把它写成 M0 dz prime, and then you can do this integration to get the final answer. 有问题？所以这是一步一步的这个步骤算给你看。所以你可以把一个这个磁铁呢，当作是绕了线圈的这种带着电流的这个元件来算它远处的磁场。OK， 好，在一般的磁性物质里头呢，它里头的这个 M 会随着位置而改变。我们上回看过这个，在磁性物质里头 ，you have some small magnetic domain. Okay, so M is a function of position. So if you look into a point function describing a B field, you do have to take into account this term that is equal to mu naught curl of M. Okay, because we're looking at some point inside a material, so we don't have to specify this V prime, this prime coordinate. So just drop it. Okay. 所以在这里呢 you have a new equation. Okay. This is curl B equal to mu naught J. This J is an isolated current. 是一个这个你加上去的电流 is an isolated current added by you. Okay, and this is the current inside a material, and this is mu naught curl of M. So let's reorganize this equation. Okay, this is something to do with a magnetic field nearby a material, just like when you calculate the electric field nearby a material, inside a material, you have to add the polarization charge into the calculation. Okay, now you add the magnetic current associated with the material into your calculation. So let's move this curl together. So you have something like a curl of B divided by mu naught minus M equal to J. This is an isolated current added by U. So this is an isolated current. Be careful, all right? Compared to the previous example for the electric field, if you still remember, for the electric field, you have divergence of epsilon naught, divergence of E equal to isolated charge, right? But if you put this electric field nearby a material, then you have to add polarization charge into the calculation. Okay, and this polarization charge is equal to divergence of P. Now you're doing a very similar step to add a material current into the expression. And this material current is equal to curl of n. Okay, now this equation is converted to divergence of D equal to isolated charge. This is isolated charge. So this equation will allow us to use Gauss law to calculate the D field given some isolated charge. So at this point, you know that you can also define a symbol that is only related to isolated current. So let's define this. Let's define this to be a new field called H. Okay, define this to be B divided by mu naught minus M. And this equation is written into curl of H equal to J, and this is a physical quantity that is only related to an isolated current. 就像你 define D， 它只跟 isolated charge 有关系。你现在 define H， that is only related to an isolated current. Okay, and we call this magnetic field intensity, H. Magnetic field intensity. 有些同学喜欢老师写黑板，所以呢，我说的 mix my slide together with handwriting， 可以吗 ？OK， 现在知道这个 H 的来源了，它是一个数学符号，为了方便计算，就像 D is a mathematical symbol for convenience of your calculation. Okay, so given this. Given this, you define H equal to B divided by vacuum permeability minus M. And previously you have divergence D equal to rho for the electric field. And once you calculate D from this isolated charge, you can get your electric field from D divided by epsilon, if you remember. How did we get this relationship? Because this D was defined to be this. And we know P, this polarization vector, in the linear regime is equal to some vacuum permeability, vacuum permittivity multiplied with some electric susceptibility multiplied with the electric field. Okay. For most materials with a small electric field, there's a linear relationship between P and E. Therefore, we can write D into epsilon naught 1 plus chi E multiplied with electric field. And this is redefined to be a new constant called relative permittivity. And you group these two together to get epsilon. Okay. And for this magnetic field, we also adopt the same approach because M, in most cases, is proportional to the current, the external current. And the external current is proportional to H right here. If I have an isolated charge, H is proportional to it. So this M in the linear regime can be expressed as mu naught H multiplied with a magnetic susceptibility. This chi m is called magnetic susceptibility.就像这个开一样，我们把它叫做 electric susceptibility. Okay, so with this, 你可以把它整理成 B now equal to H multiply with mu naught plus M multiply 这里对不起，这里没有 mu 0，这个 mu 0是没有在里头的，在这个定义里头。OK， 这个 M 跟这个 H 呢有一个 proportional factor like this， equal to mu naught chi M multiply with H。OK， 所以你注意到已经开始注意到这个观念是一样，但是呢，这个定义这个数学式子写出来的时候呢，它有一点点不一样。你看到 P is equal to vacuum permittivity multiplied with susceptibility, electric susceptibility, and then electric field. But now for this one, you recognize that I made a mistake. We don't have this. 所以你要写的时候呢，这个式子都对称，但是呢，你要注意到，并不是100%对称。OK， 好 ，Given this, then you can write down this expression like a chi m multiplied with h, and then you group this into mu r. This is relative permeability. Okay, relative permeability. And then you continue to group this into permeability for the material. OK， 所以在这里呢，你得到一个简单的结果了。这个结果就是 you first get your answer from this expression. If you want to find out the magnetic field, magnetic flux density in a problem, then once you have this result as a function of your isolated current, then you can do B equal to mu H to get your final answer. As long as you know mu r for given material， 所以呢，你可以查表查出一个物质的这个 mu r 是多大，然后呢，算出你最后的磁场强度是多强。Okay. Well, last time I told you that this epsilon r is always larger than 1. So there's always a reduction of electric field inside a material. Okay, for usual material. Okay, for most materials, your electric field is reduced by a factor larger than 1. But for magnetic field, this mu r for some magnetic material can be much larger than 1. So you have enhancement of magnetic flux density nearby magnetic material. OK， 有没有问题？没有问题，来，很清楚，写了一次给你看了。好，我们做一个简单的例子，很简单的例子。我们上回算这个螺线管。A solenoid. Okay, and then we have a B field. Suppose I carry a current like this. Then I have a B field. For this case, it's going to go this direction, B field. And this B field is equal to mu naught n I. Okay, let's do a calculation according to the new equation. This formula is called Ampere's law. 新的 Ampere's law 是这个 ，nothing to do with B now, just from this expression. So let's do an Ampere's law calculation. Forget about this for a moment, all right? And then you create a path like this, and along this loop, according to this Ampere's law, you do a cross-path integration for this edge. That dl is going to be equal to the current enclosed inside this loop. And there's no magnetic field outside. Suppose that this solenoid is very, very long. Okay? And for this, you have a uniform magnetic field intensity inside. So you have sort of H multiplied with some length. Suppose this is the length of L equal to Ni. So you have H equal to Ni. This N is equal to the total number of current divided by the length. So this small n is the density of the wires, the number of current loop per unit distance. So once you have this H, you are interested in knowing the magnetic field B, magnetic flux density B. So you can convert this H to B by doing this multiplication, because this is in a vacuum. Suppose this is in vacuum. Okay, so your B can be calculated from this. So finally you have answer B equal to mu naught Ni. You have your answer in vacuum. But this is only the first story. You have a second story that is that you put some magnetic material inside. Okay, you put some magnetic material inside with relative permeability like this big, mu r. Then you have material. So you already have H. H is only to do with the isolated current. So H remains the same. You have H equal to Ni. But now your B is equal to mu naught mu r Ni equal to mu Ni. Okay, your B field is enhanced by a big factor, mu r. This mu r can be very big for some magnetic material. 所以呢，你如果要产生强磁场的话呢，你可以拿一些这个磁性物质，像铁块塞到这个里头来，那它磁场就会大量的增加。Okay. Any question? 有问题？没有问题，来，我用这个投影片帮各位复习一下。所以 B field 跟 E field 有很大的不一样，这个概念上头 ，B field 可以因为物质的存在变得很大，但是 E field 呢会因为物质的存在而变小。那 E 的概念呢是一个 field intensity，B 的概念是一个这个flux density。所以这个 B 场跟 E 场呢有一些这个对称性在那个地方。 OK， 这是我们刚刚讲的例子哈。哇。Okay, let me review the concept just a little bit. Okay, in the material there are charges, and those charges are moving. When those charges are moving, you can generate current. For moving current, you can produce magnetic field. So for orbiting electrons, there's some sort of very small magnetic dipole associated with it. Even an electron can spin. In fact, for most of the charged particles in an atom, they spin about the axis, and there's also some magnetic dipole moment associated with the spinning electrons, charges. And in the material, usually those magnetic dipole they group together into a small domain. 有一个小范围，这个看这个物质大小，物质是什么的物质，它不是单一个 electron 形成一个 domain， 而是一群的这个 electron 它会自己纠结变成一个 domain 的这个形状。But the orientation of those domains are random. Therefore, you don't measure any net magnetic field from those randomly organized material domains. But if you have some external field to those domains, the domain will tend to reorient their direction according to the torque equal to m cross b equation. Okay, 所以呢，你这附近的这个b field can be increased. So given this, we actually deduce that those small magnetic domain and those small magnetic dipole, in fact, will contribute to some vector potential. This means that they can generate magnetic field, all right? And so now you can model the material according to these two currents. But for uniform material, the curl of M usually is 0. So this surface current becomes important because those surface current cannot be cancelled. OK， 所以呢，刚刚我们就在 model 就是这么一个 small magnet 的这个原场的时候呢，我们可以把它变成很多的这个小的电流在它表面上头，然后来做计算。OK， 把这个每个小的电流产生的 magnetic field 把它加起来，就是你最后答案。OK， so now we have to rewrite the Ampere's law. Previously, we have this vacuum expression. But with the magnetic material inside a current loop, you can realign the magnetic domain. Therefore, the B field is modified. And this B field is increased due to the isolated current, 你自己加上去的电流, and the material current. Okay, right here. 所以这个概念很清楚，哎，你一旦这个加了电流之后呢，这个里头的小电流呢也跟着在同一个方向上头。这时候呢，你要把这些所有的电流都考虑进去。Therefore, you rewrite this expression. Once you rewrite this expression, then you move this to this side, and then you define a new symbol called H, and we call this magnetic field intensity. Okay, so this is the new defined symbol H, and this H is only to do with the external current, just like D is only related to the isolated current. 所以呢，这时候呢 you can always calculate H from this isolated current, and then use this H to calculate the B field if you know the relationship between H and M. And it turns out that in the linear regime, 并不是所有的这个物质，尤其并不是所有的这个物质或者是所有的这个 H 场呢，都跟它是线性的关系。等一下我们会看一个非线性的关系。但是如果说 if this H is small, then if this current is small, H is small, then H and M has a linear relationship. 这时候呢 ，given this linear relationship, you can write this B into some constant factor multiplied with the H field, and this H field is only related to the isolated current. OK， 那在这个relative permeability 呢，在一些这个磁性物质里头可以非常非常大，100万倍，增加100万倍以上。OK， 那这是重新这个修正过的 Ampere's law。那刚刚我们做了一个柔线管的这个计算。所以这个物质对于磁场呢有很强的影响，尤其是磁性物质。那我们来看一下这个几种磁性物质的称呼。来，有些这个物质呢，其实你加了磁场之后，它反而是会这个磁性会变小。那尤其是随时间变化的磁场加进去之后，那你们高中的时候都学过 Lenz's law。Lenz's law is that if you apply a time-varying magnetic field to a system, the induced magnetic dipole moment is going to try to reduce the change. 来，这是 Lenz's law。当你有一个这个随时间变化的场放到一个磁性的系统里头的话，它 induce 这个 dipole moment 的话，会是这个要来这个抵抗这个改变。所以呢，在这种状况之下呢，这个 mu r could be less than 1 ，OK， and this is called diamagnetism。那这个是所有的系统都会有这个反应。这个 Lenz's law 就是这样子，就是都会有这种抗拒的这个反应，但通常这个效果很小很小 ，OK。那反而是所谓的paramagnetism 是比较常见的。为什么？因为这个你加了一个外加磁场在这里的话，它会让这个 domain 呢沿着你磁场方向来转动，因为 m cross b 的关系，那个 torque 的关系，所以more or less most material will have this kind of behavior that the mu r is larger than 1, but for different materials, some material is easy to reorient those magnetic domain, but some materials are not so easy to some magnetic domain are not so easy to move around. 所以呢，这个有些物质呢，这些 domain 不容易移动，所以呢，它稍微大一点，但是并不是很大。那这个东西呢，就是叫做paramagnetism，OK。那磁性物质的话是比较有趣，磁性物质的话呢，它 domain 很容易移动。你只要外加一个磁场进去的话，外加一个电流产生一个磁场 ，and then you can align most of the domain along one direction. Given this, you're going to have a very big relative permeability, and this is called ferromagnetism. 一般的这个铁块这个磁性物质的话，那它的这个 mu r 通常都是非常大。OK, a small external magnetic field intensity from a current loop aligns magnetic domains in such a material, resulting in a very big magnetic flux density B in this material. 所以呢，这个 ferromagnetic material 呢是很有趣的东西，就是一般你经常拿着这个磁铁的话，可以去吸铁块，譬如说这个铁块呢本身就是一种这个 ferromagnetic material。OK， 所以这观念性的介绍。Any question？ 我们刚刚说这个线性的关系存在于 M 跟 H。Okay, say that we have this relationship, but I phrase it very carefully. This linear relationship, but in fact, this linear relationship only exists in a small range of H. Right? H is proportional to a current, according to this expression. So basically, when we say this, we are seeing that this M is proportional to the current. Okay, But because we write B equal to mu h, we write B equal to mu h, and this is equal to mu naught h plus mu naught chi m, and this is linearly related through this. So when we say this, we are saying that the B is proportional to the current. OK， 当我们说这个 m 跟 h 是线性的时候呢，同等的，我们在说 B 跟外加的电流是线性的。But when you do an experiment, the story is different. When you measure B, given an I in the current loop, for example, in this case, if you put I, the current, into this loop, and then measure B field inside this solenoid, it turns out that you have this kind of complicated curve. So 一刚开始的时候呢，你的 B field 等于0 when you put no current into the system. Well, be careful that I put current next to H, because according to this expression, H is proportional to the current. Okay, so I can put my current into this expression. 这个 I 呢不在你的 handout 里头 ，OK， 你可以加上去。那一刚开始的时候，你不放电流的时候，你的 B field 等于0，合理 ，right？ 这个系统什么都没有。And then you put some current into the solenoid, then your B field start to build up like this. And then if you increase the current, then this curve starts to saturate. 因为当你电流加的越多的时候，等到这些 domain 都已经 align 了，你的 B field 的这个强度不再依赖这些 domain 的 alignment. Therefore, you have this situation of B versus I. 你在学一门学问的时候呢，我们东方人习惯把这个数学式子算出来，但是呢，在我们教育里头似乎就比较不强调这个解释。所以呢，我如果看你们的期中考的这个解答的话，通常就是算了一堆式子出来，完全没有任何的解释。OK， 那这个对你将来下一步做研究会有限制。You have to understand a phenomenon, a curve, an equation from the physical point of view, but not just from the mathematical expression. Okay, so when you look at this curve, you need to be able to interpret that. So you put some current into the system, and then the curve starts to saturate, because now think about that, all the domains sort of align along some direction. Therefore, the enhancement of B due to those domain is not going to be obvious. Therefore, you have a saturation of this curve. And now you reduce the current. In the backward direction, you reduce the current. Then, of course, your B field is going to drop. 但是呢，它不会沿着原来的路径回来，它会沿着这条路径下来。也就是说，你想想看，你已经到了这个饱和的状况，你要把它再把它凹回来的话，它已经排列排好了，再把它凹回来，它有些惰性，不愿意凹回来。OK， 所以呢，你不会沿着原来路线回来。You go by this curve. So when your current drops to 0, you have some residual magnetic flux density even at 0 current. 因为你没有把它完全恢复到原来这个状况，它还是 partially aligned at 0 current. Okay, therefore you have this kind of remnant magnetic flux density at 0 current. Unless you reverse the current to some value, and then you can cancel out the magnetic field, because if you reverse the direction of the current, then you try to rotate this domain, some of them, in the reverse direction. Therefore, you can cancel out the magnetic field generated from this current, from this external current, and the residual magnetic field inside this material. OK， 所以呢，你在看这个图的时候呢，要把那些 domain 在那边动的那种样子呢，想到你的脑袋里头去 ，right？ 所以呢，你改了一个这个电流方向，可以把它拉到0的地方。那这个 H field 在这个地方叫做 corrosive magnetic field intensity。那你如果继续把这个电流负的方向加上去的话呢，这时候呢，你的 B field 也会改方向了，改方向，因为你的这个 magnetic domain 原来 previously is along this direction, now the direction could be reversed because you force it to reverse。所以 B field 呢也整个变过来了，所以会掉到这一点。但是回来的时候呢，它也不是从这里回来，它会走这个 loop。Therefore, there's a finite area associated with it. Okay, and this B and I is only linear at some small location. Okay, B 跟 I， 所以这个关系式呢，其实是在一个小范围之内。OK， 那这个 loop 叫做 Hysteresis Loop。有些这个只要牵涉到机械的移动的话呢，或者是 friction 有些摩擦的话呢，这个是叫做会产生这种 Hysteresis Loop， 就是它不会回到原来的 state， 你必须呢多花点力气才会回到原来的这个临场的位置。Okay, so a hysteresis loop is a B field response curve of a ferromagnetic material under a current. Okay, 那这个 H 呢，在这里呢，基本上 according to this Ampere's law is proportional to a current. So therefore, I put a current symbol right here. 那这个，所以刚刚已经跟你解释为什么会有这个 residual flux density 跟 corrosive magnetic field。那之后我们会计算 just like we calculate the electric energy associated with the electric field, well, later on we'll calculate the magnetic energy associated with magnetic field. 所以其实这个范围里头的这个面积呢，是你会这个你放进去的能量，也就是说你到时候积分这里头面积。就是这个你放进去的能量拉动这些 magnetic domain 的这个所花的这个能量，那这个在你们课本里头有一个习题，你可以练习一下 ，OK？ But later on, we're going to teach you that the magnetic energy associated with magnetic field can be calculated from this equation. Okay, just like we calculate the electric field energy from the E field and D field. Okay. 那这个能量呢，你可以想见 ，at this moment, I only want to tell you the concept. Okay, when you move those domain back and forth, 这是 small materials. They are inside some sort of small cluster of atoms inside material. So when you move those materials around, there's some friction. 它们有摩擦力。你要把它原来是在这个方向，然后呢，你要把它翻过来。You want to flip it and then flip back force like this. There must be some friction associated with it, and collision at the domain boundaries, and that will produce heat. 会变热。OK， 所以呢，当你这个电流是来回在动的时候呢 ，you are moving those domain back and forth. Okay. And when you flip this domain, the domain wall is going to have friction and they could collide with each other to produce heat. 所以呢，你可以用这个来干嘛？你可以用这个来煮东西，这就是 induction oven 的原理。Okay, and induction oven has a coil inside it that produces the magnetic field to flip the domain wall in your hot pot， 在你火锅的这个材质上头呢， 冬天我想你们这个冬天的时候一定会用到这个东西来煮火锅。来，火锅的话呢，它只有些这个材质的火锅你才可以加热。那这个材质呢，最好就是 magnetic material。OK， 那这是你们所常见的这个火锅，叫做 induction oven。那在这个譬如说晶体成长的一些炉子里头，需要加到非常高温的话 ，very often that you use this kind of induction oven to provide high temperature。因为这种 induction oven 的话，你注意到没有火在那个地方，没有明火在那个地方，所以if you want to produce heat uniformly inside a material, very often that you use this kind of induction oven。OK， 这时候呢，你就不用烧柴或者是烧个火起来，那相当的方便。All right， any question？ 我们期中考的题目呢，我请你们回去把它当做一次作业，下礼拜3的时候交过来。OK， 回去在没有时间的压力状况之下呢，我想你的表现会更好。所以下礼拜1我们继续上课。